A little bit about me. I'm engaging in a sport called bearding. It's my #1 natural talent. This is, I think, 2-time world champion. I'm going to take this guy down. I bodyboard, so I'm in the ocean a lot, so I like to think my beard is fortified with minerals from the Pacific Ocean, and that I can win on girth because of that. This talk is based on my book from O'Reilly called Agile Data. It's a philosophy. It's not the only way, but really, it's good. So we go fast, but don't worry. The book is on the open publishing system with O'Reilly, so you can actually go back and get more in-depth stuff. If you just Google Agile Data, it's the top link. There's also a bunch of blog posts. If you Google my name, we've done a lot of examples. So in terms of building analytics applications, the Agile Development web application side of things is fairly mature. Ever since the LAMP stack happened, and there are all these post-Rails frameworks, you can set out to build a web application and have a pretty good chance of building something that your customer, whoever you deliver it to, will actually get some use out of. And then you have data warehousing, which is pretty good at solving business intelligence questions, but is very siloed. You have all these, like a data mart, a data warehouse. It's difficult to get at all the information in one platform. And then you have scientific computing or high-performance computing, traditionally very hard to use. That's UNIVAC and Deep Blue. It's funny, they kind of look the same. I don't know how many of you have ever used MPI, but the HPC stuff has traditionally been smart kid only, I like to put it. I tried to use it in college, and I was not able to do so. So what is data science? It might be the intersection of these 3 fields: application development, data warehousing, and scientific computing. And there's now this concept of data center as a computer, but because of disparities in the size of memory, disk access speed, network speed, it's actually very difficult to harness large numbers of commodity machines in a way that it behaves like a warehouse scale computer. But like Hadoop to the rescue. So you adopt Hadoop, you get rid of your silos, you dump all your data in one place, you're doing joins that have never been done before, you're doing ETL in a very modern, clean, powerful way. It's very invigorating, exciting. The silos are crashing down. You have an army of mappers and reducers at your command. It feels awesome. But now what? What new opportunities does this enable? And so it's analytics applications, predicting the future, that kind of thing. Doing this takes a very broad skill set, from customer through marketer, product manager, experience and interaction designer, web developer, data scientist, researcher. Nobody has all these skills, and so analytic application development is inherently collaborative. And so it's essential that we collaborate well to build good apps. And so there's this concept of the data science team. It's 3 to 4 team members with broad, diverse skill sets that overlap. You don't want more than 4 or 5 people because transactional overhead starts to dominate. That doesn't mean that you don't need expert researchers. These generalists, you can hire expert researchers and then they kind of spend their time lent out to generalist teams. You run it like a studio, not like a assembly line, with quite a lot of freedom, but with real goals and deliverables. And it's important to remember that in terms of productivity, work environment matters most. So, okay, how do you get insight into a product? Now what we're describing, the back end has gotten a lot thicker. And generating profitable insight can take 10 to 100 to 1,000 times as long as just throwing up a Rails app. So there's this timeline disjoint between how long it takes to build an application on the web and how long it takes to do serious analytics to drive that application. So how do you ship insights efficiently? We don't want them stuck in the lab. How can you collaborate with researchers as a developer? So there's definitely a wrong way to do this, and that's to bolt analytics onto your existing development process and say, hey, we made this great design. Your job is to predict the future for it. Hey, what's taking you so long to reliably predict the future? Okay, you did, but now the users don't understand what 86% true means. I don't know how many of you have used Flightcaster. I love this app, but 86% true is as on time as any flight ever gets. And I have trouble understanding that, and I think I have an understanding of Bayesian inference. My mom has no clue, and so it's very tricky presenting this stuff to consumers. And so, all right, you're freaking out, and the plane has run into the mountain. Which kind of reminds me of the way we used to develop software, which is the Waterfall Method, where we would have a team that gathered requirements, then there would be a big design phase, and then lower level guys would do the implementation, and then you would get to verification, but in fact the requirements would usually have changed, and so most software projects failed. This was a terrible way of building software, and I'm glad we've gotten away from it, but analytics poses challenges that sort of bring us back there. And so the chief problem is that you can't design insight. You discover insight, and you discover things by exploring. And so we might then formulate a strategy. Make an application for exploring your data, iterate and publish intermediate results, ugly stuff, stuff that's not ready for the world. And that stuff becomes a palette for what you ship. In your application, it could be a system, something. So there's this concept of data design. It takes into account the fact that it's not the first query that gives you insight. It's the 15th, the 150th, the 1500th. And you want to capture those aha moments. But with Hadoop, it's slow to do those in batch. Furthermore, if you could give someone instant SQL, really they're going to understand the insight better in a web application context, sort of that you've created. And when you're doing real research, hard research, you might direct a PhD at a tough problem, and he might work on that for like a year. But if you've scoped the problem slightly wrong, you might invest man-years and not get any use out of it. The PhD might have done his work wonderfully, but you sort of screwed up, and so it's a loss. The semantics of presenting predictions, like the 86% true thing, are complex, and you want your designer working on those from day one and not the day after you ship 1.0. And so the opportunity in analytics applications lies at the intersection of data and design. So given all this, how do we get back to agility? So a statement of principles, then tricks with code. We want to set up an environment where insights are repeatedly produced by all members of the team. That's an application that's interactive from day zero, like before you have your first Scrum meeting, you plumbed your atomic records through, and in that meeting you can click and look at them. The data model is consistent end to end, so this is essential for good collaboration. You don't want to have ORM, you don't want to change data at each layer in your application stack. You want to keep it consistent. That way you're all talking about the same thing, and you're all thinking in terms of the real data the way it is. And so as you work on that, the depth and scale of your insights grows until the application pays for itself. And so you have a snowballing audience where a researcher might share, daily or weekly with the rest of the team. Then you might publish things every couple weeks to the company, then on to the customer, then on to the public. But you really don't want to take more than about a quarter to get something out. So in this system, we value the document over the relation. This is an email from me to my father asking him to plant a cover crop at a farm I used to live on. And so you'll see in the top left, that's what it looks like in Gmail. The actual document that was sent over the wire is beneath it. And you'll see that the document presented actually looks like the document sent. And so the raw data is very connected there. As opposed to that, this is the Berkeley Enron email set SQL schema on the left, and it's my attempt on the right to recreate a document using SQL. I actually couldn't quite do it, but it's much more complex and abstract. So I would suggest that relational data is a legacy format. Why join when you can project? Storage is really cheap. You can join once, create documents, and use those thereafter. You don't do 0 joins, but you do far fewer. Then you're looking at the data in terms of its actual structure. And with new column compression formats like ORC, Parquet, Trevny, you actually get a lot of efficiency back when you have duplicate fields in your data, just as you would with joins. So in this system, we value imperative languages, like where you explain what you want to do, over declarative, where you explain what you want and rely on some engine to work out the details. We do this because we don't know what we want to select. You're usually working with data iteratively. It's dirty. 85% of your time as a data scientist is spent munging. And so imperative languages are optimized for our process, which is iterative snowballing insight. Also, doing it this way, you're not sort of beholden to a SQL planner. And if it doesn't get it right, your sort of code is stuck. You actually have the opportunity to self-optimize. We value the data flow over the select. This is an example of calculating the number of emails between two email addresses. There's some ETL there where you lowercase the email addresses. This is a bigger example of that. So what I'm getting at is we value Pig over Hive for application development. Pig will eat anything, any data. It can work without a schema or with a schema. It's optimized for refining data iteratively as opposed to consuming it as SQL is. It's imperative, it's iterative. It has data flows that are SQL-ish, but not exactly SQL. There's code modularization and reuse with Pig macros and UDFs in a host of languages, most recently R. Illustrate is a command. When you're working with Hadoop, which is a batch system, you don't want to run over the entire data set each time you develop and come up with some new line of code. And so Illustrate will actually sample the data, but simultaneously generate data to satisfy like conditionals. So if x is greater than 5, it'll have 4 and 6, and just show 6 getting through. So you can do a lot of your development with Illustrate. It's an awesome, awesome feature. Pig streaming lets you use any tool, and the point of all this is that we prepare our data on Hadoop as it will appear on the user's screen. And so there's this requirement of a local host version on some sample versus petabyte scale. We want to use the same tools and write only once. This is an absurd requirement, but it's entirely possible. So we want to use simple tools, high-level tools. If you prepare a sample with document format that we're using, it's actually very easy. With relational format, it's a little more tricky because if you sample two relations that join, the keys will miss. You'll get 0 records out of that. So you start locally on a sample, use Illustrate, iterate, and then run on the larger data set on the cluster once it runs. Skip object relational mapping, and don't trust databases. Those things don't work. Everything is rebuildable from HDFS at n equals 3. And so there's this concept of the data value pyramid, which is why bolting application development on, or analytics development onto your existing application development system doesn't work. You have to start at the bottom of the pyramid and work your way up. If you skip steps, you'll be ill-prepared to take the next step. If you're starting out with records, you plumb them through, as I said, right at your first meeting. Then you start building charts. Then you move on to reports, predictions, and finally you drive actions which create value. So step 0 or 1, display atomic records on the web. You want to serialize your documents in some kind of format. There's protobus, thrifts, JSON, objects, or Avros. I use Avro because it works well with large files. The schema is on board, so you could just load the file and not specify the schema. It's kind of optimized for large files. So you might create documents via Relational ETL. This is that the Enron Berkeley set transformed by Pig into documents. You might serialize events from streams. In the book, we actually download your inbox and then write out Avros of your emails, of your Gmail inbox. Or you might ETL logs. So step 1, plumb those atomic events through to a browser. This is a stack that I like to use. It's Kafka, Hadoop, Pig, Mongo Hadoop, MongoDB, and Node. But I don't really care what you use. There's a bunch of examples up on the web doing this kind of stuff. So all right, step 1.1, cat your Avros. Note, in Avro format, this data still looks like it originally did. It's still an email. It still looks like something you would read in your inbox. So now load the events in Pig, and once again, still an email. Illustrate the events. It's an email with some sample data. Now publish the events to a database. You can do that in one line, which is about a 4 or 6-line script. Now check the events in the database. It's still an email. This is a program, this is Sinatra, and you could easily publish events on the web in any language in about this many lines. And it still looks like an email. This is a JSON email in the user's browser. So the idea is that it's a one-liner to transition between levels of your stack. That's what a good stack looks like. All right, so what's the point of all that? The point is that now everyone can connect and work on the real data as it actually is. And when you're building analytics applications, that is the key to success. So now the entire team, including the product manager, who may have like harebrained ideas, is grounded in reality. You'll see how ugly the data is. If you haven't seen it in document format, you really aren't familiar with it. You'll see how much work you have to do. And now you can ship early and often and sort of do an agile process. So now you might wrap those events that you publish to the browser as JSON with Bootstrap to make them look like that. So this is a simple application header with just some JSON dumped in. This is a foundation, though. I don't know about you, but almost everything I've ever built before Bootstrap was ugly. Now that I build things with Bootstrap, they're kind of like okay. You know, they're not distractingly ugly, and that's where you want to get. So refine that a little bit, display the emails properly. It looks like this. Start adding links between emails. Start to list links to sorted events. So for instance, the most recent emails like you would view in your inbox. If your database can sort, you can use that feature. If it can't, you can pre-prepare lists and access them in a key value store. So that looks like this, again, like your inbox. Now here's a neat trick. If you built the interface for listing your documents, you can use Elasticsearch to make them searchable. And once you have the Elasticsearch cluster booted up, it's really like just a one-liner to get it there, which is pretty neat. All right, so moving on to step 2, create simple charts. This is an example. It's the number of emails I send per hour of the day. But you want to always start with a table, not an actual chart. The reason is there's probably holes in your data. There are probably issues that you can catch in tabular format that you might even miss once things are pretty and you're distracted. There are libraries for creating charts. There's 2 or 3 now for D3, which is sort of the prevailing chart library. What you're doing, though, when you're creating charts is you're aggregating by properties of the data, which is the first step at entity extraction. So you can now group documents by entities, rank and count, publish top N time series, and fill a page with charts. This is how you do the top N of anything in Pig. It's not a lot of code. This is how you do a time series of anything in Pig. Again, very brief. And so this is what data processing in our stack looks like. The point here is, so the guy on the left only knows Perl or Python. He's a data guy. The guy next to him knows Pig to string it all together. The guy there knows like Ruby or JavaScript, and the guy on the right only knows CSS. Each of these people can now collaborate and contribute features on their own in the way that they know. And that's great. That's when everyone is empowered and working well together. But then on general principle, because we know that our application will scale best on Hadoop, where it will scale linearly, we shove data processing towards the back of our stack. So this is an example of doing the count of emails in JavaScript, then in Python, then in MongoDB and MapReduce. Note there's a lot of code even for Mongo's MapReduce, and then in Pig. So then once you have charts, we move up to reports. We start to link entities together. So for instance, our chart page gets related email addresses as well. So you can now click on those and transition between entity pages. And so each entity type that you extract gets its own type of web page. Each individual one via an ID gets its own web page. And so you link entities as they appear in the event documents, like an email address, you can link out to its page. As you create this sort of web of interconnected documents, you're sort of arriving at reports. What you're really doing is curating interactive ontologies of semi-structured data. So you might start with a tag cloud or something and then send the user out through email addresses, times of day, that kind of thing, topics. One trick, though, because we're building indexes on the fly and they aren't shared, if you have a data set, you filter it in 2 different ways, and then you later join those back, you'll get key misses and lots of 404 errors. So it's important to remember to push filters back into a common data set that you then branch off when you want things to later join. All right, so now you've got an application, so get people clicking, get them involved, start learning. Keep trying different stuff, figure out what's interesting, clean your data as needed, and we are now in a position to start thinking about predictions and recommendations, which is our next level. So we've made charts, we've made reports, we've now extracted entities. The whole team understands the data as we processed it, so they know what we have, and there's a palette of what to build next. They got that understanding by exploring the data, and everyone is on the same page. So now we can start to think in different perspectives, like in terms of networks, time series, distributions, natural language processing, conditional probabilities, or Bayesian inference. This is a network. Bob knows Sarah, Sarah knows Bob, Bob knows Sarah, Bob likes Sarah, not too much, and then a more complex example. So anything can become a network if you just think of it in terms of connections. This is how you might create that in PIG from email documents. This is a network, which is what, I think this is my inbox visualized. Blue are reciprocal links, people that email one another. And the 2 clusters there are like Pig and Hive. Gray is people that don't reply back. This is not a very good network visualization, but you should make one anyway, even if it's not very good. People love to look at these things. They show the complexity of data, and making one will possibly get your project funded. You can build these in Gephi. It's fairly easy. Gephi is an open source project by Matthew Bestown, and it's awesome. So you might do social network analysis. This is PageRank and Pig. You might create and analyze time series and distributions, which I think we've already done. You might smooth sparse data if you have time series. Regress data to find trends. Use natural language processing to extract topics or keywords. This is using a macro for TF-IDF, which lets you use it in just a few lines of code. It's 2, in fact. So this is what natural language processing, like topic extraction, looks like. This is just a frequency count of that email to my dad in the beginning. Plant grass were each mentioned twice, so they're keywords. There's code for TF-IDF and LDA on the web. This is a man called Bayes who was incredibly naive. You can do Bayesian inference, and so we'll start to do an example of that. Gmail's feature of suggested recipients. When you email someone, they'll tell you who you might like to CC. Let's take a shot at reproducing that. So it's this much Pig, diving in a little bit. Step 1, count who I email. Get a simple count. So I email Mike at O'Reilly. I've emailed him 28 times. Step 2, count number of times I email someone and CC someone else, and then divide that by the total we just got. So you come up with a probability of inclusion. And then next, oh wait, that's actually how it works. Stop here. So when Google says they believe in large amounts of data and simple algorithms, they really mean it, and we approved it. So, okay, the probability that my wife will reply to one of my emails is 0.13. Sometimes predictions are tough to handle. But what you really want to do, though, with these predictions is enable new actions. So what we might do is some domain analysis. Why doesn't she reply to my emails? What time is best to catch her? When does she send emails? Are my emails too long? Is there a correlation between length and not replying? Do they contain original content, or am I just forwarding bills and things that aren't meant to be replied to? Are they nice? We could do sentiment analysis. Do I reply to her emails? That was like a deep moment for me. And then finally, the obvious one, do I CC the wrong people like my mom? The probability that my wife will reply to one of my emails when I include my mom is actually 0. I've calculated it. So this style of development, awesome guy in Australia picked it up at a company called Packet Loop. And they developed a system called Packet Pig to read full data captures. So they'll go in, and for your internet connection at an enterprise, they'll log every bit of data that flows across it. So it's actually cost effective to do this because most even fast connections aren't saturated. So he's able to just slap a 3 terabyte or 2 terabyte drive on and log everything. What this allows him to do is once a 0-day exploit is released, he can go back and look and run the signature and see 6 months ago when nobody knew about that exploit, were you compromised and what did they steal? Or what did they see? It's really neat stuff. And so what that ends up looking like when he processes that data is this. He's using the same stack that I just described in the same manner, though. And I know this looks really cool, but it's actually not that much more sophisticated than the Bootstrap front end. It's just been refined by a front end guy, or maybe a few weeks or a few months. So this is sort of the end state that your applications can get to, which is comforting. Thanks a lot. Now, are there any questions? Okay. Well, thank you for your time.